Thank you for tuning into this lesson from Transparent Physics. This one is on moving in circles. Moving in circles involves objects that are traveling in a circular path. So for the record, we're going to start off with a little bit of a disclaimer in this episode. Alright, so the idea is that what we're going to be talking about in this episode involves the idea of objects traveling in a circular path. Say an object traveling around a road or something like this. We are not going to be talking about objects that are spinning on an axis. Spinning on an axis is still physics. It's just not the physics that we're going to be talking about. So, let's start talking about things moving in circles. Physics builds on concepts we have learned earlier. At this point in the academic year, you've probably talked about several of these ideas already, which we're going to need in order to understand things moving in circles. So let's take a look at some of these foundational topics, foundational skills, let's say. First of all, the idea of velocity. Velocity is a measurement of an object's speed and its direction. This is a vector quantity. You need both of these together in order to understand what velocity actually represents. The especially important idea for this topic is the idea that velocity includes direction. Tying that in immediately is the idea of acceleration. Acceleration is when velocity changes. Now, this can be a change in speed, it can be a change in direction, it can be a change in both. For the purpose of this discussion, we're going to assume that the object's speed remains constant when it's traveling in a circular path. But we are going to be changing the direction of its motion. The next couple ideas involve Newton's laws. First of all, we have to remember the idea that forces exist in equal and opposite pairings via Newton's third law. Anytime there is a force acting on an object, it is the result of two objects interacting with each other. If you can't figure out what those two objects are, you might not be talking about a set of real forces, and we'll talk about the implications of that towards the end of the video. If forces are balanced, the idea that there's the same amount of force acting to the left and to the right, or up and down. If forces are balanced, that means the velocity is going to be constant. This is the idea of inertia via Newton's first law. Inertia is the idea that an object will continue to do what it was already doing, whether that's staying at rest or staying in motion. Either of those are free for physics. That's going to happen automatically. It's changing the motion of an object. Acceleration that you have to pay for with an unbalanced force. Which brings us to the second law. The second law says unbalanced forces yield a change in velocity. Remember, a change in velocity can be speed or direction, speed and direction. The focus for us is going to be direction here. Not speed, really, in the direction of the unbalanced force. So you're going to have a change in velocity in the direction of the unbalanced force, and that's Newton's second law. So those are the foundational skills that we'll need to build on for this lesson. Let's take a moment, enjoy a cup of tea. Well, maybe not the whole cup. We got stuff to do. But let's move on. Let's talk about an application of this. And let's imagine that you have a dog on a tether in your yard. And let's say there is a squirrel in play. So the dog is sitting there and it's just sort of watching what's going on, and it sees a squirrel off in the distance. Now this squirrel is outside of the range of its tether. The dog doesn't know that yet. And the tether is kind of slack right now. So the dog has an opportunity to just sort of start running forward towards the squirrel. Now as it gets closer to the squirrel, the line pulls taut. The cable can pretty much just pull inward on the dog's harness. So an inward pull, and instead of being able to go straight, the dog is moving in that direction. But instead what we're going to have is we're going to have a curve. The dog's motion is going to start tracking in this direction. Still has motion, still has inertia, but there is a force pulling it inward which changes the direction of the velocity. And then, assuming that the dog keeps at it, the dog is going to get pulled in a circular path. The tether is going to be pulling inward on the dog's harness. Squirrel remains safely out of reach, and the dog travels in this circular path. Now, this is sort of a nice example of what I'm talking about for moving in circles. The object has motion. There's a force pulling it inward, and that force results in a curved path. Putting all that stuff together, we have a reasonably good example of objects moving in a circular path for this lesson. The leash exerts an unbalanced force. It means there's a force pulling inward, but no force pulling outward. The dog therefore accelerates in the direction of the unbalanced force. This acceleration pulls the dog inward along a circular path. Anytime we have circular motion, you're going to need to have this special force, this force that's always pulling towards the center. Now, these motions can look very different from each other, and it doesn't really matter what's causing the force. What matters is the idea that the force is always acting toward the center. So let's take a look at a bit of a plethora, if you will, of circular motion. All motion along a circular path requires this unbalanced force acting toward the center. So if we take a look at a variety of motions, we can see here that we have, there's a sporting event in track and field called the hammer toss. It's sort of like a cable connected to a hammer, and there's a large mass at one end of it, and the person winds up and then releases it, and it flies 60, 70, 80 meters. The idea is that as this is spinning, they are pulling inward on the cable, pulling this mass toward them as they spin around. Another example is a car taking a turn. Car's driving, turns to the left on a, let's say, an unbanked road. The thing that keeps it going around the curve is the friction between the tires and the road. That friction is directed inward towards the center. The center of the curve is here. Center of the curve is here. Here we have an airplane. Generally, as an airplane turns, they're going to bank a little bit, which means they dip one wing down, lift the other wing up, and this creates a force, at least a component of the force that's directed towards the center of the curve. And this is basically sort of the lift force from the air. But as they turn their wings and dip one end down, a component of it is pointing toward the center of the curve. And we even have the Earth and the Moon. The Earth is pulling on the Moon. The Moon's pulling on the Earth too, but we won't worry about that for this diagram. The Earth is always pulling the Moon toward it. This motion of the Moon orbiting around the Earth is the result of an inward force from the Earth on the Moon, always directing towards the center, which is basically the Earth. So in all of these instances, even though these all look very different from each other, there's what we call a center-seeking force. Now, this force that always acts towards the center has a special name, as is often the case in science. We're going to use a little bit of Latin here. So a center-seeking force. Center is centri, seeking is petus, and put it together, centripetus is centripetal. Centripetal. Centripetal, I think, is sort of the British way of saying it. Centripetal is how we say it here in America. But centripetal force, a force acting towards the center. Now, there's another word that sounds similar to this one that a lot of people use instead. We are going to talk about that one a little bit later, but it's not centripetal. Sounds the same. You can probably say it right now, but we'll mention it a little bit later. So that's in terms of the background. Now, anytime we want to keep moving toward the center, we need this centripetal force. When the person lets go of this cable, the hammer flies off. If this car hits some ice, it doesn't go in a curved path anymore. It goes straight. When this airplane levels out, it flies straight. If the Earth was to just disappear, the Moon would fly off straight. So in all these circumstances, a force pulling towards the center is required to maintain that motion. If we don't have that motion anymore, the object will no longer move in a circular path. So let's take a look about that in action. So let's imagine that we have an object here, and we have an object spinning in a circular path. Okay, so here we go. So we got an object, and we're imagining that it is moving in a circular path. Let me get this up a little bit more for us here. Okay, it doesn't really matter what the object is. Let's say, for instance, it is a keychain on a little cable here. All right. As that object is being spun around in a circle, there is always a force acting toward the center, the chain of the keychain part of it. Its velocity is always changing. A changing velocity is an acceleration. So even if the speed is constant, which we generally assume in introductory physics, the speed can stay the same, but the velocity changes because the direction of the speed changes. Force towards the center, force towards the center, force towards the center, force towards the center. Let go of the cable or the chain or whatever it is, and this object's going to fly off straight in this direction. A lot of people would think that it's going to fly off radially. It won't. The object has inertia. It's going to keep moving in the direction where it was going. So we're going to try to use a little bit of the document camera's abilities here. Let's see what we can see here. I'm going to zoom out, and we are going to set up a little mini lab here. All right, so we have our keychain, me, and I'm going to spin this object around. Now I am constantly pulling inward on it, and if I let it go, it flies off. And if we have a chance to slow-mo this and take a look at it, I don't know that I'll be able to do that right now, but I'm going to try, and if I can, I'll probably edit it into the video right here. And if I let it go, so hopefully you just saw me editing in a slow motion version of that. If not, hey, try it on your own. It's spinning around, and when I let it go, it flies off. When I lift my finger up, it no longer moves in a circular path. This idea of a force being required in order to keep something moving in a circular path is very important to what we are discussing. So if we take a look, now this seems like we are learning new physics here, but we are not. This is just an application of Newton's laws. If you've been studying Newton's laws throughout the year, you've probably been talking about them up to this point with objects moving in a straight line. This object is moving in a turn, but it is the same idea. The idea here is that we have any motion in a circular path is considered acceleration. I know sometimes you probably think of acceleration just as a vocabulary word you need to memorize, but it is a benchmark condition that we need to watch out for in mechanics, because if something's accelerating, it has to be accelerating for a reason. Acceleration is not just a vocabulary word. In this case, in all cases, acceleration means the velocity is changing. In this case, it's the direction of the velocity that's changing. Even if the speed's staying the same, if the direction of the speed is changing, it's still considered to be acceleration. And you cannot have acceleration, whether it means speeding up, slowing down, or changing direction, unless you have an unbalanced force. If for any reason this unbalanced force, this force acting towards the center, which we have called the centripetal force, if that force stops or is terminated, the object will continue to move straight with its current velocity. It's not going to fly off radially. It's going to keep going straight. That's its inertia. And again, that's free. That's automatically going to happen. When people talk about an object moving in a circular path, or they share their experiences, maybe they took a turn hard in their car, or they went to an amusement park and rode a spinny ride, those sensations involve the feeling that you're being pushed to the outside of the curve. A casual observation of this might lead one to believe that there is a force that's pulling this key chain out to the outside. All right? That there is a force pulling it outward, and that when I let it go, I let the force pull it away. In fact, we don't need that at all. But that idea is very common thinking, and it matches our sensations. When you're riding an amusement park ride, you feel like you're being pushed to the outside of the curve. This idea is another word from Latin. We've talked about centripetal. Let's spend the last part of the lesson trying to talk a little bit about centrifugal. Now, centrifugal force is a little more complicated in the idea that a lot of people think it's real. And even the way I say it's not necessarily fair to it. Centrifugal force is real. But it's not helpful for talking about what we want to talk about right now, because we're worried about the forces acting on you as you go in a circle. So, but if you're traveling in a circular path, or objects around you are traveling in a circular path with you, it seems as if there is a force that pushes them to the outside of the curve. If you have sunglasses on the dashboard of your car, they will seem to slide to the outside of the curve. If you are riding in an amusement park, you will slide to the outside corner of the seat. It's natural to think that there's a force pushing to the outside. There's even that trick where you could take a bucket of water and spin it over, sort of in a vertical loop, and the water doesn't slosh out of the bucket out of the top. How does that work? It's a little more complicated, but a lot of people will say there's a force pushing the water up. The problem is that this application of centrifugal force is incorrect to use to explain what we're observing. You can explain everything in the context of what we've already talked about in terms of centripetal forces. And I'm going to try to share with you, to wrap up, 3 strikes against using centrifugal force to explain how this motion occurs. Let's imagine again that you have an object, you're driving, you turn to the left, and you or your sunglasses say slide to the right. Strike 1 in using centrifugal force to explain that is the idea of inertia. Inertia tells us that an object wants to keep doing what it already was doing. We don't have to pay for that. There's a force pulling to the inside, force pulling to the inside, force pulling to the inside. That force terminates for some reason. Whenever that happens, the object continues to move straight. The important thing here is to recognize that this doesn't cost us anything. We've actually been paying a price to keep it to move in a circle like this. If we lose that force pushing to the inside, it no longer changes its direction of motion. It just does what it would do anyway and continues to move straight. This is free. All right? You don't need an extra force to keep doing what you were doing. That's free in inertia. That's the concept. That's free in physics. It's the concept of inertia. So to argue you need a force pushing you to the outside is an incorrect interpretation of the physics. You do not need a force pushing you to the outside. To the quote-unquote outside of the curve is the direction you would naturally go anyway. You need a force to keep you from going out of the curve. Second strike is the idea of looking at the physics closely. If you want to make the argument that there is a force pushing these glasses to the right when you turn your car to the left, you're allowed to do that. But what's the origin story, as I like to say? What is the cause of this motion to the right? We can take a look at the forces. I did a little free body diagram here already. We've got the normal force acting up. That's the surface of the dashboard pushing up on the sunglasses. Gravity pulls down. And then we can even argue that there's a friction acting to the left, because if the glasses are sliding to the right, friction is going to act to oppose that slippage. So is there a force that pushes these glasses to the right? If there is, you just have to tell me what object is acting on the glasses. Forces are object A interacting with object B. If you can find a force that's pushing these glasses to the right, be my guest. But right now, it doesn't appear that there is one. So, strike 1, you don't need a force pushing you to the outside because that's the direction you'll go anyway. Strike 2, there actually doesn't seem to be a force pushing you to the outside. And strike 3 is probably the hardest one. Unfortunately, I've left a relatively small corner of the paper in order to try to explain it, but let's see what we can do. The idea is that we live in a world where generally you are not accelerating. You are generally either at rest or, say, moving with a constant velocity. On occasion, you speed up. On occasionally, you slow down. On occasion, you change directions. But that's not generally how you spend your life. Now, yes, technically, we are on a globe that's constantly spinning in on its axis and traveling through space, and the Earth is always accelerating. But we are inside of that, what we call frame of reference, so we generally don't feel it. So let's just argue the fact that we are not accelerating every moment of our lives. When we do accelerate, our brain tends to interpret our sensations in the context of as if we were still at rest. Example, let's say we are in an elevator. When the elevator accelerates upward, you're on the ground floor, the elevator speeds up to carry you to the top of the building. During that short interval where you're accelerating upward, you will feel heavier. Do you actually gain weight during that process? No. And again, I could spend an entire another video on this. Maybe I already have, depending on what time you're looking at this on the channel. But the argument is that this is your weight. Your weight is constant. It's mass times gravity. Now, in order to accelerate upward, you need to have an unbalanced force. So the elevator needs to exert more force up on you than the weight is pulling down on you. Assuming the elevator does this, the floor of the elevator, you're 600 newtons, the elevator exerts 700 newtons on you, the elevator wins, you accelerate upward. You feel heavier because the floor is exerting more force up on you than you're used to. Under normal circumstances, you're standing on a sidewalk, somebody puts a heavy backpack on you, you're going to feel the sidewalk push up on you with more force than your weight. So your brain interprets that as, I'm heavier now. Similar sensation when you're in an elevator, but no one needs to put a backpack on you. You're just going to have the floor exerting more force up on you in order to accelerate upward. You feel like there's more force pushing down on you, when in fact, there's actually more force pushing up on you. Moving in a circular path is the same general concept. You, as we've talked about earlier in the video, have a force pushing you to the inside of the curve. You have this force acting on you from this, let's say it's an amusement park ride, you're riding some car that's traveling in a circular path. This is the outer wall of the amusement park car. The car is pushing you in towards the center. As a result, you push the car to the outside. This is Newton's third law. This is perfectly natural. Not natural, it has to happen. The car pushes you inward, you push outward on the car. Does that mean there's an outward force pushing on you? No. You are pushing outward on the car is pushing in on you. Now this sensation that you're feeling though, makes you feel as if you are being pushed to the outside, because under normal circumstances, if you're just sitting on a bench somewhere and you feel pushed against the side of the bench, it's probably because somebody's pushing you into the side of the bench. In this case, there is no force pushing you to the side of the bench. You are actually trying to go straight. The bench is pushing you inward. No, not the bench. The amusement park ride is pushing you inward. The sensation is that you're being pushed to the outside, when in fact, just like the elevator, it's 180 degrees off. You are not being pushed to the outside. You're being pushed to the inside. It is the inside push that allows you to maintain that motion. If you were to lose that inside force, that would be a problem. You would go straight and probably be a lawsuit somewhere in there. I do want to end with a little ode to centrifugal force. When I was a younger teacher, I used to say centrifugal, F is for fake. I used to say centrifugal force really isn't a real force. That was unfair of me. Centrifugal force is a real thing. You can have a force that acts to the outside of the curve. This red arrow here is technically a centrifugal force. The car is pushing you in towards the center. You're pushing out on the car away from the center. No matter where you are on the ride, you're going to be pushing out on that car. That is a centrifugal force. A centrifugal force is simply a force that's always acting to the outside. And it's a natural thing to see when things are moving in circles. But it doesn't generally affect the object that we are interested in. So I want to end by saying centrifugal force is a real thing, but it doesn't act on you during circular motion. Since it doesn't act on you during circular motion, let's just focus on centripetal force. That's what's going to help us out. And but if you hear somebody talking about centrifugal force, I'd bet pretty good odds that they're using it incorrectly for the three reasons that we talked about here. All right, let's do a quick review of what we talked about in this lesson on things moving in circles. So much I can't fit it in the camera all at the same time, but let's take a look here. So to review, we are interested in objects moving in a circular path, not objects that are spinning. In order to focus on the material correctly, we did review the idea that velocity is speed and direction, and it's direction that's really the important thing, because changing direction is an acceleration, just like speeding up or slowing down. Forces have to be in equal and opposite pairings. We talk about that a little bit later when trying to debunk centrifugal force. If the forces are balanced, the object will keep doing what it's doing via its inertia. If the forces are unbalanced, the object will accelerate in the direction of the unbalanced force. So all of Newton's laws come into play. I'm sure you're used to the important role that Newton's laws play in introductory physics. A dog on a tether tries to move straight. A force pulls inward, pulls it in a circular path. This is repeated again and again and again and again. Anytime you have an object moving in a circular path, you need a force pulling towards the center. No matter where the object is in the track, it has to have a force pulling towards the center. This center-seeking force is what we call a centripetal force. Centripetal force always acts towards the center. If you lose the centripetal force, you lose the circular motion. Flies off straight in the direction where it is going. That is free. Moving in a circular path costs you an unbalanced force. Moving straight is going to happen due to an object's inertia. This idea that an object wants to move into the direction of the outside of the curve is often conflated with the idea of a force pushing to the outside, which people call a centrifugal force. There is a centrifugal force, it just doesn't do what you think it's doing. The centrifugal force is not pushing you to the outside of the curve. You will naturally tend to move towards the outside of the curve because you're going to want to try to travel straight. When the object you're riding in takes the curve, there is no force pushing you to the outside if you actually look at the forces acting on you. Although your brain will think that, because your brain tends to incorrectly interpret acceleration as happening as a result of forces that are opposite of what's actually occurring. I appreciate you taking the time to tune in to this lesson in transparent physics. We'll follow this up with some practice problems. We'll take a look at the equations and the math associated with the physics. Until then, thank you for taking a little bit of time to see things more clearly with transparent. Oh. I almost made it all the way through. With transparent physics. I screwed up the closing line. How about a haiku?